Welcome to the course on advanced power electronics. We'll cover today permanent synchronous motor drives. The outline of presentation, working principle and types of permanent synchronous motors, then permanent synchronous dynamic modeling, and then control of permanent synchronous motor, vector control, sensor like vector control, direct torque control with sensor, sensorless direct torque control, then permanent synchronous motor high speed operation, sliding mode observer based sensorless control, predictive control, loss minimizing control, fault control, and case study of PMSM drive related to power quality improvement in PMSM drive and design control of solar PV fed PMSM drive for solar pumping, and short example and numerical and references. So coming to the basic of permanent synchronous motor drive, how the basic is there. So on the stator we have a normally 3-phase winding, maybe of course other than 3-phase, 2-phase or 4-phase also, but usually 3-phase winding. And on the rotor we put the magnets in different forms, maybe buried or maybe surface mounted. So there are a lot of categories. This is the basic idea, and you can have a more detailed configuration here, that how the rotor we have sometimes LNC also. When this is a new concept with the flux barrier, where we put a rare magnets which will also work like air. So we have a both good torque, especially for electric vehicle industry, a very good torque due to silency as well as typically due to permanent. And however, we have a inverse silency in this case here, because on the direct axis we put permanent, but the air gap is quite large, so that the you can call it the LD is lower than the LQ. That's why we call it inverse silency. But on the rotor it's very smooth, so it's normally preferred for electric vehicle for high speed operations, like as you can see here. Like, so now these are typical configuration. If you talk about permanent, so either you can have magnets on surface mounted, or you can have interior build with the neutral concept of these two. And there are plenty of applications of this, typically in industry, like industrial drive, like pumps, fans, blower, compressor, centrifuge, mills, hoist, etc. as you can see typically. And then machine tools applications, because it's one of the most efficient and very accurately controlled. Then servo tools, then the automatic presses, then the internal transportation system in the industry as well as at the airport, or in the typically in various industrial production. Then the robots, it's also used in information and office equipment, computers, then the printers, then the plotters, scanners, and facsimile machines, photocopiers, audiovisual aids. Then domestic life, it's used kitchen equipment like refrigerator, microwave oven, dishwasher, because of very high efficiency of these motors even for low power. Then the bathroom equipment like shaver, hair dryer, toothbrush, massage apparatus, and washing machines and clothes dryers, humidifier and dehumidifiers, then lawn mowers, pumps for irrigation, swimming pool, etc., including the solar pumping. Then toys, electric vehicle, and the vision and sound equipment. Then cameras, security system, typically automatic door, etc. Then vacuum cleaners, elevator and escalators in transportation, and in transportation people movers. Then light railway and trams, as you can see, aircraft flight control. Then the electric ships, because of most efficient, and electric aircraft, the electric boards. So these are the you might have seen the lot of applications of the PMSM. And for especially permanent synchronous motor application, electric road vehicle have been, you can call it 75% industry are preferring the permanent synchronous motor for typically like electric road vehicle. Now even a Tesla started using PMSM. Earlier they were using induction motor, and typically Nissan Leaf, they are also using permanent synchronous motors. Another model of then Chevrolet Spark also use permanent synchronous motors because of high efficiency at different loads. Then the Chevrolet Spark, another model. Then another model of Chevrolet Spark. Then typically two-wheelers, high rating two-wheelers, especially interior built permanent motors with the 82 kilowatt motor for these two-wheelers, of course at high speed at 5000 rpm. Then your 0S F7.2 two-wheelers, another model of this, and then the another 0DS, another model of typically of two-wheelers, another model of two-wheelers. Then Kia Soul also use interior varied palm magnet synchronous motor. Then Kia Soul also use your interior varied synchronous motor. Then Kia Soul another model. Tesla model, of course, they use for front motor palm magnet synchronous motor. However, they use at the rear still induction motor. Then the Tesla another model they also use, and Kia e-Niro also use palm magnet synchronous motor. So a lot of electric vehicle manufacturers are using this. Then in power tools for the drills, hammers, and screwdrivers. Then power tools like grinder, polisher, saw, and hand pieces because of brushless construction as well as very high efficiency construction. Then sanders and sheep shearing hand pieces. Then for public life, heating, ventilation, and air conditioning system. Then catering equipment. Then coin laundry machines. Then auto bank machine, auto vending machine, money changing machines, and ticketing machines. Then barcode scanner and at supermarket. Then environmental control systems and clocks, amusement park equipment. Then medical and healthcare equipment, especially dental hand pieces, dentist drill. Then electric wheelchair, medical and healthcare, in air compressors. Then rehabilitation equipment, artificial heart motors. Then in defense application in tanks, missiles, in defense forces. Then radar systems, submarines. So now I hope by this time you are already convinced why you use this palm magnet synchronous motor. These palm magnet machines virtually can be classified in two categories, with cage rotor, without cage rotor, it's cageless rotor. So it can be magnet, can be inset kind of magnet, or surface mount, or interior buried magnets. So typical examples here of magnet structures are here surface magnet, as you can see the magnets are on the surface, and second case it is inset magnet. Then your typically interior magnet and of two flux, typically flux concentration, and then surface synchronous PMSM surface mounted magnets, as you can see here. Then with a lot of typical models of your surface mounted typical geometry, as you can see, probably many geometry with surface mounted for low speed application. And then interior palm magnet, as we discussed for electric vehicle, and many other typical rotor geometry, especially with the flux barrier. That another geometry is a typical rotor geometry. Then this interior palm magnet synchronous motor, you can say in different electric vehicle with the Pyrus 2003, Prius 2004, Prius 2010 and Ford model. Then Cheru World, Honda Accord, Camry 2007, Lexus 2008, and Leaf. So what is the kind of the rotor construction? And you can see in that, of course, stator is normally 3-phase winding. So another type of construction is axial flux machine. So machines are constructed that have flux flowing along the axis direction of shaft, and they are known as axial flux machines or pancake machine in industrial circuit. So you can see on the A on left side, where we have a rotor typically geometry on one side, and then we have a stator typically with the coils shown in between, and then in the B side we have a typically on stator on both the side, and typically we have a magnets rotor assembly on the rotor side. So sometimes rotor is only with the magnets are bounded with the synthetic material, so it's very light, especially as well as it has a very low inertia. So it's used normally kind of disc motor with the very high performance, or you can call it the very servo drive kind of applications, and with the high efficiency like. And this is typically how it look like a typically stator assembly as well as rotor, PM rotor in between. And then the other side, other construction is that PM rotors are on both sides and stator is in between. Or these are the another construction, claw pole rotor type palm magnet axial alternator, which are used in most of the, even all electric vehicle for the generating the electricity for charging the battery, even normal car or normal truck. So it's a brushless construction, a very compact construction with a small size, weight and volume. And another this type of magnetic axial field alternator. So now coming comparison between your typically surface mountation with the interior kind. So there is like a PM location normally on surface mounted surface, but in interior permanent is in cavity, permanent fixation with the glue or band, and that is in case of interior bed inserted. Field harmonics on PM is large for surface mounted, is small in case of interior bed. PM usage large, and typically in case of surface mounted relatively small. Saliency ratio is 1, but in case of interior bed it is more than 1. And reluctance torque, of course, is not there in case of surface mounted, but in case of interior buried, large synchronous reluctance torque is available. And power density, of course, is high in case of interior buried magnet, and speed range for field weakening is large, of course, interior magnet. So because of this, I mean, most of the application for high speed as well as with typically we prefer interior buried or interior magnet synchronous motor. Now coming to principle and operation of magnet synchronous motor. So based on the interaction of sinusoidal back EMF waveform and sinusoidal armature current waveform, the magnet synchronous machine has balanced three-phase sinusoidal distribution of air gap flux and sinusoidal distribution of armature winding. So magnet synchronous machine operation, magnet synchronous motor winding has a balanced three-phase sinusoidal pattern for back EMF like E, A, B, C. E is cos omega ET, E is cos omega T minus 1 2 by 3 or E cos omega T minus 4 5 by 3, and balanced three-phase sinusoidal current I, B, I, C, I cos ET, omega ET, I cos omega T minus 2 pi by 3, and I cos omega ET minus 4 by 3. And then the total electrical power is equal to P total equal to EIA plus EBIB plus ECIC. And PM synchronous machine operation for power output is E into I in bracket cos square omega T plus cos square omega T minus 2 pi by 3 cos omega T minus 4 pi by 3 unit power factor. So it becomes EI by 2 in bracket 1 plus cos omega T plus cos 2 omega T minus 2 pi by 3 plus 1 plus cos 2 omega T 4 pi by 3. So it becomes 3 EI by 2. Thus the shaft torque is equal to T omega R, that is 3 EI upon 2 omega R. And since back EMF is E equal to KB omega R as shown here, and the power for individually all three phases, so total power for three phases becomes constant 3 by 2 EI, and torque becomes 3 KB by 2 into I. So now this is basic model of permanent synchronous motor. You can see clearly the surface mounted magnets on three phase winding on the stator as is symbolic. Now coming to typically PMSM dynamic modeling. So permanent, I mean, taking in case of two pole, we have a typically on the left side a figure that we have a D axis flux path and we have a Q axis flux path, and of course with surface mounted we already talk about LD is equal to LQ. So applying for surface mounted synchronous machine inductance, applying the Pierce law at the D axis, so we say B upon mu M, mu PM into 2 is HM plus B upon mu 0 2G plus B upon mu FE L core equal to NID, and where mu F equal to 4000 mu 0 in case of electrical steel, and B0 B upon mu Fe into I core is relatively small, hence the neglected. Since mu PM is almost equal to mu 0, so we obtain B equal to mu 0 N upon 2 in bracket G plus HM into ID, and the air gap area through which the flux crosses A equal to half pi dr into LST, where dr and LST are the diameter and stack length of the rotor respectively. Then phi equal to NB into A into LDID, where N is the number of turns of the D axis winding, and the D axis inductance LD is equal to mu 0 N square A upon 2 in bracket G plus HM, and so similarly the LQ is mu 0 N square A upon 2 into G plus HM, and it's LD equal to LQ. So this is typically the case of flux path interior permanent synchronous motor D axis path and Q axis path, where LD is smaller than LQ because the typically the magnets, where the magnets are placed, you have a more air gap. Magnets also we have like a air gap, like especially rare earth, silicon, cobalt, and indium and boron. So now the inductance is LD equal to mu 0 N square A upon 2 in bracket G plus HM, and LQ equal to mu 0 N square A upon 2G. So thus LD, you can call it, is much smaller than LQ for this type of interior buried permanent synchronous motor, and this inductance asymmetry generates the reluctance torque. So typically now coming the flux linkage of a phase winding for different rotor position, as you can see here how really the flux varies with the typically with the theta, and the effective air gap and its inverse function of g theta as well as 1 upon g theta. So coming to now dynamic equation. So surface mounted synchronous motor in stationary frame d upon dt, id iq in stationary frame equal to minus rr, rs upon ls in bracket id upon in id iq minus phi m omega e ls in bracket minus sin theta e cos theta e plus 1 upon ls vd and vq. So this surface mounted machine frame, it becomes, when we transform synchronous reference frame, it becomes d upon dt id e2 id iq in bracket minus rs upon ls omega e minus rs upon ls into id iq minus omega e ls 0 1 plus 1 upon ls vd e and vd vq. Now for interburied permanent change model in stationary frame, vd and vq equal to rs ids iqs plus in bracket ls minus 3 by 2 L delta cos theta e minus 3 by 2 L delta sin theta e minus 3 by 2 L delta sin theta e and ls plus 3 by 2 L delta cos theta e into d upon dt id iq minus 3 omega e ls in bracket minus sin theta e cos theta e in cos theta e and sin theta e id iq plus omega e phi m in bracket minus theta e and cos theta e. The I am in synchronous reference frame d upon dt in bracket id and iqe in bracket minus rs upon ls and omega e ld upon lq upon ld minus omega ld upon lq and minus rs upon ls and into id iq minus phi m omega e ld lq in bracket 0 in 0 1 plus 1 upon ld vd and vq upon lq. So now coming to typically rotor flux linkage expression phi m equal to ld if, and you can see the equivalent circuit for d axis and q axis. So d axis consists of your vd rs omega e lq iq with the ld and with the current source if equal to phi m upon ld, and then the another current source vq e, then rs omega e ld id plus phi m and then lq. So now the developed torque is obtained as T equal to 3 by 2 P by 2 in bracket phi m IQ minus LQ minus LD into ID IQ, and phi m is the electrical, phi m IQ is the electromagnetic torque based on the Lorentz force, and LD minus LQ is the ID IQ is the reluctance torque caused by the LD minus LQ asymmetry. And for the lossless model, VD equal to minus omega E LQ IQ and VQ equal to omega E LD ID plus omega E phi m. So the total electric power is P equal to 3 by 2 in bracket VQ IQ plus VD ID equal to 3 by 2 omega E in bracket phi m IQ plus LD minus LQ minus LD into ID IQ equal to 3 by 2 omega R in bracket phi m IQ plus LQ minus LD into ID IQ. So mechanical equation is given T equal to J omega R upon dt plus P omega R plus TL. So now this is the typically block diagram representing the PMSM dynamics, where we apply a VDVQ and then we have a block corresponding to your 1 upon LS LD as RS, which give the IQ, and then we have a cross coupling omega LD for the term for reference and omega LQ, and then this goes back to, so then another for VQ 1 upon LQS plus RS, and then we have a typically vacuum up that your omega R P by 2 into phi m, and it goes with the ID IQ followed by reluctance torque LD minus LQ multiplied the current, and then phi m IQ, that's another torque due to electromagnets, that is reluctance into 3P by 4. It goes to the typically then the minus low torque is go to the input as a mechanical part 1 upon JS plus B and give the output as a omega R after this transfer function. So coming a typical PMSM drive structure, we have a 3-phase inverter and feeding the PMSM which is coupled to the load, and we are sensing the position for giving to DSP for the control, and of course we sense voltage and current of the motor and form the command input. By calculating the algorithm, we give the gate driver for the inverter circuit like So now coming to control technique for PMSM drive. The PMSM drive can be controlled by scalar control, vector control, director control, sensorless vector control, acyclic director control. So coming to scalar control for PMSM drive. So the control of PMSM drive requires a continuous rotor position information. Therefore, the scalar control of PMSM drive without position feedback signal is a tough task. That is open loop or true synchronous mode scalar control. And scalar control of PMSM in self-control mode can be implemented with or without motion sensors. The sensorless control of PMSM is self-control mode using torque angle increment compensation for torque variation during the tangent. So now coming to true synchronous mode of permanent synchronous motor drive. The true synchronous mode of operation is employed only with the voltage source inverters in practice, and voltage source inverter may be of 6-step or PWM which contains harmonic. Because of low impedance of the damper winding, the harmonics contained in the armature current will be high, resulting in a losses and torque pulsation. And increasing the impedance of damper windings reduces the harmonics current but reduces the effectiveness of during hunting. So when the torque pulsation are unacceptable with 6-step inverter, a PWM inverter may be used. And due to hunting and stability problem, the true synchronous mode with PMSM drive is employed only in a multi-machine system requiring accurate speed tracking between the motors, that is spinning mills, paper mills, and textile mills, etc. So the delay circuit is employed to ensure that the change in inverter frequency is slow enough for the motor speed to track the revolving field speed. And since all the motors are connected in parallel to a common inverter, their speeds are uniquely related to one common frequency. Now coming to scalar control topology of PMSM drive. So in a scalar control, typically we have a frequency with a delay circuit, and that we go to a flux control for deciding the voltage, and from that we decide the firing angle of thyristor converter, we decide the DC link voltage, and of course from the frequency we give to inverter control for changing the inverter for PMSM drive. So this is simple VSI fed permanent synchronous motor in open loop, and this is typically again VSI fed. So here we use this, of course VSI we can use the multi-motor drive. So we have a frequency again which can give a control to inverter driving a many motor, and of course with the frequency control, frequency for flux control, and we decide the reference voltage which with the give the firing angle control for thyristor converter to decide the DC link voltage. Now coming to self-control mode of permanent synchronous motor drive. So this is of course have a permanent VSI fed. So we have a reference speed, we have a speed sensor for the feedback, and we have a DC speed converting to angle, and then from the speed we get the frequency as well as a voltage, and with the angle we are able to frequency, angle and voltage we give to the voltage source inverter for typically closed loop control, which get the almost from diode rectifier constant voltage. So it give a PWM control for this PMSM drive. Now this is typically cyclo converter fed synchronous motor with self control. So we have a reference speed, we have a feedback speed from encoder, and that this speed error with the amplified give a straight magnitude of a straight current, and this straight current decide the typically the flux. So from flux and current, and then we of course from the encoder we get cos theta sin theta, and we get the template UA UBVC for deciding the three-phase currents IA IB IC from the, and then it given to the current control of cyclo converter. Then similarly it goes to the similar way, it goes to matrix converter. So here also we encoder and we have a reference speed, feedback speed. The error goes to this block to controller which gives the reference current, and from current we get the flux, and from this encoders we get cos theta sin theta, we give the controller which give a UA UC, and with these variables input we get the three-phase reference current which really modulate into the motor winding by matrix converter proper control. Then we use typically the current source inverter also used for that. So we have a speed sensor again from a reference speed and actual speed error we give to the controller which gives our ID, and we have a feedback DC link current, and from which we control the firing angle for the control rectifier to decide the current DC link current for the current as a current source, and from frequency and power angle we are able to get frequency and angle for the this typically cycle converter in the cycle converter current source inverter feeding your permanent synchronous motor drive. Now coming to vector control of permanent synchronous motor drive. The principle of vector control is generation of three-phase voltage as a reference vectors to control the three-phase stator current. as a vector and transformation of three-phase time and speed dependent system into a two-dimensional rotating coordinate system, and this results in time invariant torque and flux, which allow control of motor with conventional technique as in a DC motor. And these are typically how the performance there. So interaction between the rotating stator flux and the rotor flux produces a torque which will cause the motor to rotate, and the rotation of rotor in this case will be at the same exact frequency as the applied excitation to the rotor. Then here, of course, we call it what is the bandwidth. You have a sinusoidal voltage, you have a sinusoidal current, you get the constant torque. So of course, you have a no torque and it give a better dynamic response and need good knowledge of the rotor position. So that is one of the reason that this preferred nowadays even for like electric vehicle, because it does not have a torque pulsation and give a better torque. Now when ID is forced to 0, then T equal to 3 by 2 P by 2 lambda F into IQ, and that is Ke IQ, where K equal to 3 by 2 P by 2 lambda F, that motor constant. So using a reference frame transformer, the PM synchronous motor can be controlled like a DC machine, and these are typically the block diagram of your vector control using coordinate transformation. So we have a normally resolver and resolver to digital converter, and multiplying the P by 2 we get the theta I, virtually cos theta sin theta I, and from the current from theta I we convert for IDIQ in synchronous reference frame, and we have it from the controller IDIQ, and then we use PI controller with feedback, and we get VDVQ, and from this angle and VDVQ we get the VS, VBS, VCS for the control of the inverter for typically through the gate drive. So coming to vector control of PM with sensors. So the palm synchronous motor have a palm on the rotor, but the analysis a high, but for the analysis a high energy palm synchronous PMS and palm may be replaced by a fictitious winding carrying a constant field return, and the input quantity to synchronous machine shall be the stator flux lambda star, lambda S star, and then field excitation current I star, and the electromagnetic torque T star. So however, because of the field current is adjusted to a predetermined value according to a given power factor, the inputs to the machine reduced to only 2. For generally the case of silent pole field excited synchronous motor in the stator flux orientation is considered. So coming to like optimum torque per ampere control. So this control strategy enforces the torque angle control for the optimum machine and the inverter utilization and maximum torque, and this control scheme requiring higher stator voltage results in poor inverter utilization, and this control is preferred for highly silent machine. Coming to now unity power factor control. So this control is achieved by controlling the torque angle as a function of motor variable, and this control implies that the VA rating of the inverter is fully utilized for real power input to the permanent synchronous motor, and the torque angle had to be greater than 90 degree, as the angle less than 90 degree will result in an increase in the flux and therefore magnetic saturation. Its implementation require motor phase current and motor parameters like LD and LQ, and this control is independent of rotary speed. Now coming to field weakening control. In this method, the induced EMF is constrained to be less than applied voltage by weakening the air gap flux linkage, and the field weakening is made inversely proportional to the stator frequency, so that the induced EMF is constant and will not increase with the speed. And this method has two approaches, direct and indirect, and the direct approach determines the value of demagnetizing current by rotary speed only. However, in the indirect approach, it is derived as a function of rotary speed and electromagnetic torque. Now coming to constant mutual air gap flux linkage control. So in this control, the resultant flux linkage of the stator Q and D axis and the rotor position as mutual flux linkage is maintained constant, and it is maintained at a value equal to the rotor flux linkage, which enables the stator voltage requirement at low value. And in addition, by varying the mutual flux linkage, provides a simple and straightforward flux weakening for the operation at speed higher than the base speed, and the torque per ampere is less than the unity and power factor is close to unity. Now this is the typical phasor diagram, stator and current space phasors and the excitation flux of the PMSM, where you have a alpha axis with the theta r, you have a D axis of the rotor, and then at the quadrature you have a Q axis, and at alpha axis to 90 degree you have a beta axis, and then you have stator current corresponding alpha. Now this is the typical case of stator current is space pressure in case of optimal operation of base speed region, typically motor operation and braking operation in the two cases. And then space pressure PM in field weakening region with the upper speed range where the ID is introduced, and then the phase diagram of operation below the base speed in first case and the operation above the base speed with the field weakening. Now there is a block diagram of rotor oriented control PMSM where we have a typically a position control, then speed position controller, rotor position control gives a reference speed, we have feedback speed, and then we have rotor speed controller that gives the reference torque. We have a feedback torque, and then we have torque controller, which after the limiter we decide the torque current reference, and from the field weakening of from the voltage we decide the ID reference, and using a lag compensation we go for ID IQ reference, and from which after the angle transformation we get the ID IQ in stage reference frame, which is converted into three-phase currents, and then we have current control PWM inverter. Like of course in actual current also for feedback are used with the transformation. And this is typically the steady state phase diagram of interior permanent synchronous motor, where you have a typically the saliency and field flux density distribution. So now coming to typically a stir flux oriented control of this. So here the you can again we have a typically position feedback, and we have a typically sense of three-phase current which convert ID IQ into station reference frame. With the position we convert into synchronous reference ID IQ, and from which from the flux parameter of the machine we get the phi SD phi SQ, is from which flux angle and its angle delta, and from flux we go to the typically the with the multiplying the your actual current we get the torque, and we have got torque controller which get the ISI reference, and then we have a flux. From the torque we have a flux also reference, and from flux feedback we get the stir flux controller. So we get the typically a delta EX, and from this we get the reference current and feedback current, and we have a current controllers for getting a station reference frame current, synchronous reference frame current. With the theta we get a direct access in synchronous station reference frame, and which convert into three-phase your three-phase winding current. With the current control we give excite the permanent synchronous motor. And this is the characteristic implemented as a function of FG1 and FG2. How it is really for the torque and the current is shown typically phi flux reference with the torque and reference torque, and the current x-axis current with the y-axis current. Like typically the torque control of India permanent for constant torque region. So we have a torque reference from which we get the ID IQ, and from the position we get the convert into station reference frame or ID IQ, and convert three-phase reference current, have a current control for rotor field oriented control mode. And this is the rotor typically with incorporating the flux weakening. So we have a reference torque, and we have a typically the position feedback, and from position we really sense the actual current, we convert ID IQ. Then of course we have a coupling corresponding to ID IQ reference, and then we get a ID IQ in case of synchronous reference frame. Then with the theta we convert three-phase reference current for current control of the this permanent synchronous motor. And this is the vector control structure of permanent with field weakening. So we have a reference speed on which we decide the flux. Above base speed we have field weakening, below base speed we keep a constant flux, and from the typically the speed controller is the torque, and from this flux we get the typical IQ, and from this field weakening of course dividing LD we get the ID. So from ID IQ we convert into your from position your three-phase current, and with the feedback of three-phase current we generate the current controller, decide the getting signal for the three-phase inverter. And this is about the field weakening, how we have it with the vector control structure from field weakening. So we have a speed, position, and we have a position controller, then the rotor speed controller, and that gives the reference torque, and from flux weakening controller we get the ID, and from here we get the after limiting we get the IQ, and then we have a typically from this ID IQ we get the after the lag compensation we get ID reference IQ reference, and with the theta we convert ID IQ in station reference frame, which convert three-phase current for current control. From this of course taking current feedback we get ID IQ from actual current and give for feedback current control. And this is typically the background current control. So we have a reference speed and feedback speed. With the speed controller we get IQ, and we have ID decided by the field weakening controller. With the position we convert three-phase current, and from feedback of current we get current controller to give to the inverter. And this is typically for the your voltage control mode. So we have a reference speed, program voltage control. So we have a reference speed and feedback speed, and we have a speed controller which gives us typically IQ star and ID. We get the pump field weakening, and from HL current we get the to transform with the theta IDIQ, and from this reference IDIQ with the voltage control we get VQ star reference voltage, which convert with the part transformation. We convert into three-phase voltage, which give to with the pendulum controller to give the getting signal to the inverter. So coming to now different topology for vector control of PMSM drive with speed sensor. So we have here, resolver or an encoder with the rotor position sensing, and which we calculate the speed, and we have a speed controller which gives the torque producing component IQ, and from speed we get a field weakening ID star, and taking a ID IQ feedback we get the PI controller we get VQ star, and from torque transformation, inverse torque transform we convert into V alpha beta. This we give to space factor modulation block, which give the getting signal, and we sense the current, two currents, and we convert into alpha beta, and with the angle we transform into IDIQ, which is used virtually for current controller. And similarly we have for current source inverter. So from speed controller we get the torque reference, and from position speed we get the IDIQ, and from this we have a current limiting. So we have convert from IDIQ from theta R we get the I alpha beta. That in inverse clock transform we get IIBIC with the space virtually space vector model, and we give to current source inverter. And of course, with the current limit we have to get from the rectifier control with the feedback of ID that control the DC link current as a current source to feeding the current source inverter. And this is for typically a current control voltage source inverter. So we have a position sensor, and then we calculate the speed. We have a field weakening controller as well as a speed controller. We get IDIQ, and that from theta we convert II into IIBIC, and sensing to current. We have a feedback current, and we put the three-phase current controller for voltage source inverter. Assuming that this voltage source inverter is operating at high switching frequency. Then we have a cycloconverter fed drive. So we have a resolver or encoder. We get the angle, rotor angle theta R, and from this we get the speed, and we have a speed control which gives us IQ, and then from HL speed we get ID star for field weakening block, and from typically sense IDIQ we have a PI controller for VQ star, and then we convert from part transform V alpha beta, which convert a three-phase voltage by clock transformation, inverse clock transformation for cycloconverter drive to give a reference voltage. And of course we sense the two-phase current which we convert into I alpha beta, and then from theta R we convert into IDIQ, which is used in the control. Similarly for matrix converter, here also we have a encoder resolver to get the position theta R, and which convert into speed. So we have a speed controller which gives the torque producing component IQ star, and then from field weakening control we get ID star, and from actual IDIQ we have a PI controller for VD star VQ star out, and from this by inverse clock transform we get LV alpha beta, which with the inverse clock transform to get VBVC for duty cycle control of matrix converter, and we sense two current which convert into I alpha beta. With the part transformation we convert into IDIQ, which is used in this control. Then similarly we have a voltage control for PMSM with magnitude angle resolver. So we have from resolver the theta R, and from theta R we get the speed. So for speed control we get the torque producing, and from field flux we get the ID as well as IQ. And then from magnitude angle we calculate the angle as well as the magnitude, and from this we have a current synthesizer to get IIBIC star, and we get sense the two current, and we have inverter control logic for current controller. So this is here how we get the from ID and IDS IQS through the resolver. We get typically IQS, that is IDS square plus IQ square under root, and gamma equal to 10 inverse ID upon IQ. So the use of resolver treats IDS IQS as inputs, and the magnitude of the resolver will become current command of for current source inverter. The angle output of the resolver will become as a gamma command, and will be fed to the phase regulator to be combined with the rotor position function, and the combined theta R and phi signals will set the phase of the current vector IQDS in the rotor reference plane. And this is typically the block means with the analog ADMC DSP board where we have a position with the resolver to sin theta modulation. We have a reference speed which give to the DSP, and typically in the DSP we have a speed controller which give with the, of course, with the resolver we get the speed, and speed controller give the torque reference, and flux controller give ID, and from ID IQ we get the IQ also, and from theta we get the three-phase current, and we have a sense current, so which give a output as a current control for pendulum for the port for getting signal for the VSI. And this is the typically schematic diagram of resolver primary and secondary. So we have a primary on side which we excite by 7 kilohertz, and this at the typically at the output like S4 S5 we get the high frequency modulated sin theta cosine theta wave corresponding to that, and we get the position. If we really demodulate, we get the position cos theta and sin theta corresponding to that, like from the secondary windings. And these are typically demodulation circuit for obtaining resolver position signal. Typically from the input signal. And these are experimental setup of control circuit for vector control, typical permanent synchronous motor drive. And the experimental power circuit for vector control synchronous motor. These are the simulated experimental performance for the typically starting of PMSM with the PI controller, vector control PMSM drive. And this is typically your experimental simulation result for speed reversal with PI controller based vector control drive. And this is typically again the torque application response simulated and experimental, how the current increases typically for the period. And this is for again removal of the load. And this is the experimental response of PI control based vector control steady state operation. Now coming to direct control of torque control of permanent synchronous motor drive. So direct control of PMSM drive, it is a direct control of the inverter states in order to reduce the torque and flux error within the prescribed band limit based on the errors between the reference and the estimated value of torque and flux. So advantage is reference frame transformation not needed, current control are not required, and pendulum unit is not required. The precise position of rotor magnets is not mandatory, only 60 degree sector wise information is needed. So problems, of course, in DTC, difficulty to control torque and flux at very low speed, high current and torque ripple, and variable switching frequency, and high noise level at low speed, and lack of direct current control. The solution is use of improved switching table and use of comparators with and without hysteresis at 2 or 3 level, and implementation of direct torque control scheme for the constant switching frequency operation with PWM or space factor modulation technique. Use of fuzzy or narrow fuzzy technique, and use of sophisticated flux estimator to improve the low speed behavior, and use of variable duty ratio control. So now there are 4 schemes: direct torque control of electromagnetic torque and stator flux linkage using an optimum voltage switching lookup table, and direct torque control of electromagnetic torque and direct access stator current using optimal voltage switching lookup table, and direct torque control of electromagnetic torque and reactive torque using optimal voltage switching lookup table, and direct torque control using a predictive algorithm for switching voltage vector selection. So coming to first, direct torque control of electromagnetic torque and stator flux linkage using a optimal voltage switching table. You can say 6 active vectors, and 0, 1, 0 vectors you want to use it. And this is typically the direct torque control of electromagnetic torque with optimal switching. So we have a torque reference, and we have typically the estimated torque from which we get the let's say the torque error, and from typically the torque control output we get the flux reference, and from actual flux we get the flux errors, the 2 level and torque level 3 level, and from this and with your sector we get the optimal switching vector table for voltage source inverter feeding the magnetic synchronous motor drive. This is the direct torque control of electromagnetic torque and DXS current using optimal vector switching. So here we are sensing the position, and typically the 2 current we convert into ISA ISPD, and using a theta we convert IGH2, and from this we get transformation we get IGH2, which we control with the DXS reference corrective access, and typically we get the even from the torque form estimating from that, and we get the 3 level torque comparator and 2 level current controller, and we get D3, and from theta we get the typically optimum switching vector selection for voltage source inverter. These are direct control of the electromagnetic torque and reactive control, and reactive torque control using optimal switching table. Here switch vectors are there, and then this is a control scheme. So direct torque control for the electromagnetic torque, reactive control is in torque reference is there. We have a reference torque, we have a reference torque and we have a reactive reference torque, and from voltage and currents we estimate the torque, both active torque and reference torque, reactive torque, and then we have electromagnetic torque controller and reactive torque controller. We give two errors, and with the sector we get the optimal switching vector selection table for voltage source inverter. And this is the schematic diagram direct control. So we have a reference speed, we have a speed sensor, so we have a speed controller, we have flux controller, and we are estimating the from voltage and current, DC link voltage and the current. We are estimating the sector, torque, flux and speed, which go to as a typically torque and flux go to torque 3-level hysteresis control and 2-level flux control, and from sector we are able to get optimal switching table. Of course, we require for estimation also, because from DC link voltage we have to estimate, and the output of this switching table is a switching typically signals for the SASPSC for the inverter control. Like, so now modeling of direct torque control PMSM die consists of modeling of speed controller, modeling of field weakening controller, and modeling of torque and flux hysteresis comparator, modeling of flux and torque estimator and sector selection, modeling of voltage source inverter, and modeling of permanent synchronous motor die. Now, modeling of speed controller is similar to that of vector control. The modeling of field controller is below base speed we keep a reference flux equal to lambda as reference equal to lambda, and above base speed reference flux is a function of your actual speed. So lambda as reference equal to lambda rated into omega b upon omega r absolute. And now coming to your modeling of the torque and flux hysteresis comparator, the flux error is given delta lambda equal to delta reference minus actual delta, and the torque error is your delta t equal to t reference minus t, and output of the hysteresis comparator can be defined as if lambda s minus lambda is less than delta lambda, then d lambda is equal to 0, in lambda reference minus 1 greater than delta lambda, then the delta d lambda equal to 1. And similarly, modeling of torque and this, if t reference minus t is less than delta t, then the t equal to delta t minus 1, and t reference equal minus t equal to the delta t is equal to delta t, then the t dt equal to 0, and if t reference minus t is greater than delta t, then dte equal to 1. So now coming to modeling of flux estimator and selection table, the lambda alpha equal to integral of v alpha minus ri alpha dt, and lambda b equal to integral v beta minus ri lambda to dt, where v alpha and v beta can be obtained from reference frame transformation as v alpha equal to minus vb plus vc and v beta equal to vb minus vc by root 3. So now modeling of similarly I alpha I beta obtained from reference current transformation, I alpha equal to minus ib plus ic and I beta equal to ib minus ic upon under root 3, and the estimated flux is under root lambda alpha square plus lambda beta square, and developed torque can be estimated t equal to 3 by 2 p by 2 in bracket lambda alpha I beta minus lambda beta I beta. So modeling of the flux and torque estimate, if lambda for sector selection, if lambda alpha is greater than root 3 lambda beta and lambda alpha is greater than 0, then sector 1. If lambda alpha is less than under root 3 lambda beta and lambda alpha greater than 0, then sector 2. If lambda absolute lambda is less than root 3 lambda beta, then and lambda is lesser than 0, then sector 4, sector 3, and if lambda absolute lambda is greater than root 3 lambda beta, then lambda alpha is less than 0, then sector 4. If absolute lambda is less than under root 3 lambda beta, absolute value of lambda beta, then and lambda alpha is lesser than lambda beta is also less than 0, then sector 4, 5, and then if lambda alpha is lesser than root 3 absolute lambda beta and lambda alpha is greater than 0, lambda beta is less than 0, then sector 6. Now coming to modeling of VSI similar to vector control, modeling of PMSM similar to vector control, and this is a table of optimal switching we call it. So where we have a 2-level flux error d lambda is 1 and 0, and 3-level torque error dte, that is typically 1 0 minus 1, and from this we get the according to the sector like theta 1 theta 2, these are the sector 6 sector, and we get the switching function from typically v0 to v7. And this is the typically the VSI fed block diagram of direct torque control. So we have a here with the voltage source we have a angle, and from which we get the speed. So we have a speed control, and for actual speed we get the torque. Speed control we get torque reference, and the field flux control we get flux reference lambda star, and we from from current and this position we get the torque and flux linkage, and from these flux linkage and reference flux linkage and torque, reference torque and feedback flux, we get the 2-level torque control and 3-level flux control. We get the DE and D phi, and with the sector we get the give to table optimal switching to decide the switching signal for voltage source inverter. And this is typically how the flux holograph and typically voltage vectors are there. 6 vector vector, all vector. So your V7 and V0 are all 0 vectors. V0 means upper lower 3 switch are on, and V17 means upper 3 switch are on, and remaining of course are the 6 possible combination of switching of 3 legs of inverter. And this is coming to current source inverter, the DTC drive. So here what we have a from encoder we get the position, and from position we calculate the speed, and from responsibility we have a give to speed controller which give a torque reference T star, and then from speed we get the flux reference, and typically for the current controller we decide the DC link current. From the rectifier convert feedback current we decide the current reference for current source inverter, and from this typically from the torque and mesh torque with the 2 level we go to table of optimal switching for deciding the you are getting signal for the current source inverter for PWM type. So in CSI based DTC, the state estimator calculate the subtangent flux delta lambda dash equal to lambda s minus LC is, where LC is the commutating inductance, and the hysteresis flux lambda S is the estimated as discussed in the earlier slide of VSI PMSM type, and table of optimum switching shall be given here with the holograph is shown in the next slide. So here you have a torque level 3 level and then 6 sectors, and you get the current vectors, and here also you have a typically your 9 current vector, 3 are 0. And now coming to cycle control fed drive. So here also we have position feedback, we have a reference speed and estimated speed. So we have a speed control to a torque reference, and from speed we get the flux reference, and from the currents and typically from the position we get the flux and torque, and then we have a 2-level flux controller and 3-level torque controller, from which we get T and D phi, and from sector we get the from table optimal switching we get the switching signal for cycle control drive feeding your PMSM. Now these are matrix converter for DTC. So we have a position, and from position we get the typically the speed, and from speed controller reference speed we get the torque reference, and from speed we get the flux reference, and from current and position we estimate the torque and flux, and from this we then reference flux and torque we go to the 3-level torque controller and 3-level flux controller. So we get the DTE and D phi, and from flux sector we get table optimal switching for space factor modulation to give a signal for matrix converter. And this is typically the implementation of DTC drive. Here we get of course the from resolver we get sin theta cosine theta, demodulator we get sin theta, and we sense the DC link voltage in the process, and sense current we get estimate the torque and flux, and from speed we get the reference flux, and from speed control we get the reference torque, and from estimated we get the getting signal for this DTC based drive. And this is the response simulated and experimental response for starting with the PI controller. You can see how the speed increases and current reduces, and this is for reversal. The response experimental and simulated response, and this is for load change application removal. This is also removal, and this is for steady state condition of PI controller for. And this is the of course estimated from current and the estimated pi alpha beta, and this is the holograph of pi alpha pi beta, which is a complete circle estimating that the is a sinusoidal flux. Now coming to sensorless control of PMSM. So now sensor reduction in vector control PMSM drive. The speed sensor has several disadvantages from the viewpoint of overall cost, reliability and noise immunity, and position and speed estimation techniques are required for elimination of mechanical sensors used in conventional drive, and for elimination of voltage sensor which is required for the measurement of PMSM stator winding applied voltage. Methods are required to reconstruct the voltage waveform with reduced or without voltage sensors. Now coming to typically a mechanical sensor reduction technique. So these are technique back EMF based position estimation technique and monitoring the applied stator voltage and resulting winding current based estimation technique. So observer based sensorless estimation of position and speed, and high frequency carrier signal injection method for estimation of position and speed, and filtering based sensorless estimation of position and speed, and current and voltage model-based SLS algorithm, and artificial intelligence position and speed estimator. And these are typically the, you can call it a position estimation, advantage and disadvantage and shortcoming, the relative for all these 7 techniques. Sorry, a simple and robust technique is investigated to estimate the rotor speed using the sense current in 2 phase of PMSM and DC link voltage, and the method used for estimation of speed comes in the category of open loop estimator and needed the sensor current of the any 2 phases and reconstructed DC voltage from the sense DC link voltage. So now coming to mechanical sensors, the position is derived from the back EMF signal and speed is obtained from the derivative of position signal. So now coming to speed of the rotor is estimated omega r equal to in bracket pi alpha p pi beta minus pi beta into p pi alpha divided by pi alpha square plus pi beta square. So here the omega r is the speed of the rotor PMSM in electric and radian, p is the derivative operator equal to d upon dt. And these are stator current and flux linkage space factor for unity power factor. And these are stator flux linkage estimation. So we get the voltage, electricity and the current, and from this voltage and current we are able to get flux with RS minus subtracting. Similarly for Q axis also we get the pi SQ, pi SD and pi SQ, and from pi SD SQ we get the d pi S DSP, and from taking this position we are able to get USX minus RX and USY this, and then taking derivative we get omega S and pi S then the angle, and then from this output as a transformation we get pi SD and pi SQ. And then similarly for open loop estimator by mounting this, so we get again the stationary reference frame voltage and current for D and Q axis, we get pi SD, pi SQ. From this we get the magnitude and angle of the flux and angle of it using the integral. And this is the open loop estimator by mounting stator voltage. This schematic diagram of speed sensor. So we sense the current. So we have a reference speed, feedback speed with the speed controller called torque reference, and ID we keep 0 below base speed, and we have feedback ID, and this error goes to the current controller for D and Q axis. We get VD reference, VQ reference, and from a position we get the VA, BBC reference, which space factor modulation for switching of this inverter. And of course from current we get the IL pi beta, and from position we get IDIQ here. And of course from DC link voltage and switching signal we get V alpha beta, and from the two current I alpha beta we get the mechanical speed as well as the position for control of this model. Coming to the extended Kalman filter, the main design steps are selection of time domain machine model, discretization of machine model, and the determination of the noise and state covariance matrices Q, R, P, and implementation of the discretized extended Kalman filter algorithm tuning. Coming to now selection of time domain machine model, space state variable x dot equal to ax plus bu and y equal to cx, where state vector x is IST ISQ omega theta r transport, and output vector y equal to IST ISQ transport, and input vector u equal to USD USQ and UP as a transform. Now coming to typically the state matrix A equal to minus RS upon LS omega r 00 minus omega r minus RS upon LS 00 and 0 and 0 omega r 0, and beta input matrix is beta cos theta upon LR sin theta upon LS 0 minus tan theta LS cos theta LS minus 1 upon L 0 and 0 and transformation matrix C equal to cos theta minus sin theta 0 and sin theta cos theta 0, and from this the voltage vector AG or UDST UV, and from this torque we get from the T from transpose we get, and from the X we get the again 1 upon P, then get the X, and then through C we get the Y. So block diagram of time domain space model of the, and time discrete space model of the X is a function k plus 1 equal to ADXK plus PD k UK and YK equal to CTK and XK, and this is a block diagram of this YK is obtained from the UK from the proper feedback. Coming to time discrete space model of the film, the space factor is distributed by the noise vector P, system noise vector, and X is a function k plus 1 ADK plus 1 XK plus PDK into UK plus VK. The optimum vector measurement vector is distributed by noise vector W, so YK equal to CDK XK plus WK, and this is how this is modeled into the block diagram. of action requirement. And implementation describe the experiment cultivate is the structure. So we get have UK, and from BK we get the feedback and back feedback, and we get the Z inverse XK. And with the CK we get the typically the WK, and from feedback in the second block also we just put EK and then feedback with the BK we get the again Z inverse XK. So coming to topology for essential factor control of PMSM die. So this is typically a PSI pad. So we sense the typically two current and two voltage, and we estimate the position and speed, and we speed control with the reference torque, and from speed we get the IDIQ, and from estimator from IDIQ we have a typically the VDBQ, and from theta we use the Clark transformation to get P alpha beta, and from Clark inverse transformation we get VA VBVC to give the switching signal for the voltage source inverter with the sinusoidal modulation. And this is with the typically the control, you can call it the current control. So we have sense current voltage, and we estimate the position and speed, and from speed control we get torque reference, and from reference speed we get IDIQ, and then from theta we convert I alpha beta. From Clark inverse we get IIB. We have a sense current, so we have a PWM generation with the current control mode. And this is with the cycloconverter control with sensor. So we have a sense voltage and current. We can estimate the position and speed. The speed control we get the reference torque, and from speed we get the IDIQ reference, and then we have estimated IDIQ, and we have a current controller to get VDVQ. Then we use the inverse part to get V alpha beta, and then from Clark inverse Clark we get V alpha beta for control of cycloconverter. And similarly for matrix converter, so we have again sense voltage, sense current. So from which we calculate position and IDIQ, and from position we get a speed, and then speed controller we get the torque reference, and from speed we get torque reference and speed we get IDIQ star, and from estimated IDIQ we go to the typically current controller, from which we get the VDVQ reference, and then from position we have inverse Clark transformation, and then V alpha beta star we get the Clark transformation VABVC reference voltage for duty cycle control of matrix converter. And then for the current source inverter, similarly we have a sense voltage current, so we get estimated speed, position and speed, and then speed control give a torque reference, and from speed we get IDIQ, and from position we get I alpha beta, and then inverse Clark transformation we get IIBIC, and we have a sense current, and we go to the space factor modulation for giving the switching signal for PWM current source inverter. And of course from current limiter we go to the rectifier, the reference DC link current, and we have a this thyristor converter with the feedback current to control as a current source from DC link. Now coming to topology of sensorless for sensorless direct or control of PMSM die. So this is typically with the voltage source, so we sense the voltage and current and get the speed, position and speed, and then speed controller, and from speed we get the reference flux and torque, and then we have estimated torque and flux and position. So from which we got 3-level torque controller and 2-level flux controller to get DTE and D phi, and from position we get the sector, and then we go to your table of optimal switching to get the switching signal for voltage source inverter. And similarly we go for this direct or control for typically of current source inverter. So we have a sense voltage current, from which we get the position, torque and flux estimation, and from speed and reference speed we get the speed control out with torque reference, and from speed we get the typically current reference, and with the current limiter we go to the rectifier to typically to control the DC link current for as a current source, and then from torque and estimate torque we go 3-level table optimal switching for current source inverter, giving a switching signal. Similarly for cycle converter for direct or control, so we have a reference voltage, we sense voltage, sense current, get the position, torque and flux linkage, and then from position we get a speed, and from speed controller as a reference speed feedback get the torque reference T star, and from speed we get the flux reference, and from this flux reference and sense estimated flux and torque we get the typically 3-level torque control and 2-level flux control, we get DTE and D phi, and from sector we get the from table optimal switching we get the signal for cycloconverter. And similarly for matrix converter for direct or control we have estimated voltage and current, and from we estimate position, torque and flux linkage lambda, and from position we get the speed, and from reference speed and feedback speed we get the you put the for speed controller to get the torque reference, and from speed we go to flux controller to get a flux reference, and from estimated flux and torque we again give to 3-level torque control and 2-level flux controller to get the dt and d5, and pump sector position we get go to optimal switching to be wave switching signal for space vector modulation of mat system. And this is the typically the result of sensorless vector control PM7 die, here experimental and simulated with the position and speed estimation response of PI control based vector control. So you can see the reversal, I mean how the position signal estimated an actual signal, and how in experimentally also is similar signal, like of course in experimentally average. So this is typically starting response in sensorless control mode, simulated and experimental result. This is for your load application and removal in both the cases, and this is for typically for the reversal. So you can clearly see how the typically reversal taking place from your minus 200 radian per second to plus 200 in experimental and simulated, and current phase is change. And this is typically your I alpha, your steady state voltage, typically the speed and reference speed and two-phase current. And this is again for starting with the you can quality estimation response of direct torque control, and this is for starting response for direct torque control, and this is for sensorless typically the load application load removal, and this is for reversal for simulated expand, and this is steady state waveform for sensorless direct torque control. So now coming to like sliding mode observer based position sensorless model predictive control of PMSM drive. So here you have of course sensing the typically two current and converting from position to alpha I beta, and from I alpha beta, and from switching signal and DC encodage you are getting E alpha I beta, and from E alpha I beta from transformation you are getting position and speed, and from speed control we get ID IQ, and ID we keep reference, and from position we convert again back to I alpha I beta, and we sense I alpha beta, we go to finite control control set of model predictive control and cost function, so we get the switching signal, I mean typically for the our voltage source in model. And this is the block of your sliding mode observer. So we have a V alpha beta 1 by S LS, and from feedback we get the typically I alpha beta with the feedback I alpha we go to the limiter, and KSW we go to the low pass filter to get the back E alpha beta, from which we can find out the typically position and speed also. And this from E alpha E beta we get the position and speed from this estimator in using NS quadrature phase local law. And this is the flowchart for your typically a finite control set model predictive control to get the typically the position and speed like from DC encodage. And of course these are the parameters of the motor on which these are implemented and simulated of 3 kilowatt motors. And these are the typically dynamic performance of the PMSM drive for typically like your current, stator current, then the torque and DQ current, and similarly for typically starting as well as the speed response change the position, HL position and the estimated position, and HL speed and estimated speed. This of course the hardware setup for indicative way of a hardware setup, and this is the typically the even open loop ramping and PLL tracking and initially startup region. And this is for sensorless for closed loop of speed operation, and then the transition from ramp mode to fully sensorless control mode. And this is performance of PMSM drive under steady at 350 RPM and dynamic step change for a wide speed range. Now coming to your PMSM high speed operation. So this is typically up to base speed we have a the power large volume, and then we have a typically the motor one we have a typically a same power but for high speed with the reduction of gear, and the second case size comparison of high and low speed operation motor. So of course high speed motors normally have a smaller volume, and low speed motors are large volume because of this torque and power relation. Of course we use the typically the gears there. To consider the PMSM dynamics, so VD in synchronous transmission, VD equal to RSID plus LD dID upon dt minus omega E LQ IQ, and VQ equal to RSIQ plus LQ dID upon dt plus omega E LDID plus omega E phi m. And in high speed region, neglecting the ohmic voltage drop lossless model and doing this, VD equal to minus omega E LQ IQ, and VQ equal to omega E LD ID plus omega E phi m, and with the phasor diagram typically without resistance drop. And typically for extending the constant power range, the voltage limit is described by VD square plus VQ square lesser than VSC square. That is the supply voltage limit of stator, and then IQ square upon VSC square upon omega E LQ square plus IQ plus IF square divided by VSC square by omega E LQ square less than 1, and the current limit is described with ID square plus IQ square less than ISC square. So in high-speed region, neglecting the ohmic voltage drop lossless model and assuming the steady state operating condition, you can see how the current limit and voltage limit of various speed in the current plane when LD is less than LQ and LQ is more than LQ. And these are constant current and power pulse in three cases. Phi m is greater than LDIS and phi m equal to LDIS. And third case is the phi m is less than LDIS. So corresponding power and speed characteristic, and then voltage limit and on current limit like. So coming to magnetic and reluctance torque, to fix the typically for the students. So ID equal to minus IS sin beta, IQ equal to IS sin beta cos beta, and IS equal to under ID square IQ. So beta is tan inverse minus ID upon IQ. And these typically you can call it the torque, reluctance torque, then the magnetic torque, and then the total sum, the two torques. So torque consists of magnetic and reluctance torque LD less than LQ, and the torque sum considering the magnitude of reluctance torque for LD greater than LQ. Now coming to current control methods, so Q axis current control, maximum torque per ampere control, maximum power control, maximum torque oblique flux control, and combination of current control methods and unity perfect control. So coming to current control methods, so maximum torque per ampere control, that's called typically MTPA. The method of maximize the torque for a given magnitude of current by varying the current angle beta and cannot be applied above the rated speed due to the voltage limit. So now maximum power control for the above the rated speed, the power maximization problem in the field weakening region is stated as maximum P equal under C1 IDIQ less than 0, C2 IDIQ less than 0. So C1 IDIQ equal to ID square plus IQ square minus IS square, and C2 IDIQ equal to eta square IQ and plus I in bracket ID plus pi m upon LD square minus VSC square omega square divided by omega square LD square. So now coming to maximum torque plus control, so applicable to the last step in high speed operation when IS is greater than pi m upon LD, and at extreme high speed the voltage limit sink to point minus pi m upon LD and 0, as the operation point is minus pi m upon LD and 0. And this is typically maximum torque plus control. So you can see the how really the flux positions are there corresponding to IDIQ axis. Like now, combination of control method considering the interior permanent synchronous with the specification given here. An example of interior permanent magnet with number of 6 poles, 8.8 kilowatt mode 3 DC voltage and base speed 2600 with the inductance 3 and 6.2 millihenry and current of 40 ampere flux 0.094. Now, this is a combination of control. Combination of control strategy. O is MTA, from OTA, A is virtually the by MTPA, and AB is maximum power, and BC is maximum torque per flux. And this is interprogramming versus speed versus torque for power plot, power and torque power. These are for combination of control for field weakening, because in case of like electric vehicle, we go for a very high speed, also like a 35,000 RPM, but up to the base speed is hardly typically 2,600 RPM. And this is the for current and angle control. So you can say with the speed how the typically the total current and the variation of beta and IDIQ. Coming to loss minimizing control for interior permanent synchronous motor. For high speed all we use the interior permanent due to silency. The copper loss is caused by stator coil resistance. PCU equal to 3 by 2 RS IS square equal to 3 by 2 RS ID square plus IQ square, and loss is PRN CFE omega lambda in bracket lambda D square plus lambda Q square, where your gamma is equal to 1.5 to 1.6 and CF equal to 1.5 to 1.6. So still load loss is for PSTR equal to CSTR omega square in bracket ID square plus I square, where CSTR is the still loss coefficient, and the total loss PT equal to PCU plus PRN plus PCR, and we have steady state relation lambda D equal to 1 upon omega in bracket VQ minus IS RSID, and lambda Q equal to minus 1 omega VD minus RSIQ. A typical example of PMS loss and flux saturation, the example of PMS MDI. And these are the parameters of PMSM drive with the maximum output power 80 kilowatt and 11,000 RPM, of course, for electric vehicle. And this is typically the other parameters. And these are the measured steady state flux per se DQ current and the access linkage and Q access flux linkage. And these are the measured value of LDLQ. And when IQ and IQ 160 and LQ and LD versus IQ and minus ID, ID is minus 160 IQ. And these are flux line accepted by ID and IQ. And these are your typically the loss minimizing control for interior permanent synchronous motor. We have a resolver for position, and then we get the speed and torque for torque lookup. Then we go to the algorithm for from DC link voltage we get ID IQ star, and from sense current we transform from position to typically AD convert to ID IQ, and we have a current controller. We get a reference typically VD, you can call it VDVQ, and with the speed coupling we get the reference speed, reference voltage VDVQ, and from position we get converted into three-phase voltage VA star VB star VC star for field domain inverter control. Of course, we have a sense current to get the DQ, and this is a photograph of experimental setup. And these are loss minimizing current ID IQ for different speed and torque found by experimental scanning method. And the loss minimizing ID IQ with fixed speed 1000, 3000, 6000 by torque is increasing. And this is the efficiency map of the IPM, your interior permanent synchronous motor. And this is the loss component between your typically your power with for different control like MTPA or your loss minimizing control. Now coming to fault tolerant operation of the PMSM drive. Fault tolerant control drive, here we have a typically three-phase motor with the, of course, with the track, and for the taking for 4-track control, and this is typically for switch converter topology during the post 3-phase fault. And these are the back voltage states, healthy inverter and 3-phase fault inverter. And this is the typically the block diagram of vector control system program with the fault tolerant inverter control. Here we have a reference speed, position, and ID IQ control. We get the 3-phase reference current direction for giving a switching signal. And these are the, of course, vector in the healthy inverter and the 3-phase inverter, faulty inverter, healthy inverter, phase fault, phase B fault, and phase C fault. And these are the parameters of this. And this is the simulated performance with the healthy inverter. For starting of the motor, how the frequency of the current increases and your switching of inverter and torque virtually change. This is the case of system when a phase fault at 2.6. Then coming to typically fault tolerant PMSM fault, when voltage phase is isolated, the dash curve is shown here. And this is typically the when the schematic of PMSM equipped with the fault tolerant inverter configuration considered. There we of course use the more number of devices. And these are typically pre-fault solid and dashed line with the fault mode VB solid and VC solid. How it should look like with the constant magnitude. Now going to fault tolerant operation of 5-phase PMSM drive with short circuit inverter fault. So it's a 5-phase. Of course, we use the double. You can call it as a single phase inverter for each phase. Like a H bridge. And here we have a torque reference, and we have a current and position sensing, and then current controller with PI controller. We get the reference voltage converted into and park inverse transform. We get ABC, and with the fault and healthy we accordingly switch on. So maybe 1-phase, 2-phase, there is still the drive will work properly with no problem. That is a typical fault is there. So reconfiguration of particular lag in case of inverter short circuit. And this is a typically how the you can call it the voltage of star connected, and typically voltage limit in short circuit fault with simple configuration. Coming to case study, typically like power quality improvement in permanent synchronous motor drive. So we have a main topology, like we have a simple as a original case of diode rectifier, then we have a LC filter, then we have a series third harmonic filter, then we have a filter with the capacitors. So here with the diode with DC link capacitor, the conventional rectifier consider diode with the DC link capacitor, and the modeling equation of capacitor voltage and rectifier can be given PDC equal to I1 minus CVDC, and PI1 equal to V1 minus VDC minus IR1 upon L1, and V1 equal to absolute VS and bracket SA minus SB, and the AC mains current IS and DC link current are calculated IS equal to SA minus IB into I1, and IDC equal to in bracket SAIA plus SBIB plus SCIC, where V1 is absolute value of VSI. One is the current flowing into the parallel combination of capacitor filter and load, and L1 is the small parasitic inductance, R1 is the resistance of the small parasitic inductance, and IS is the AC mains current. So SASB are the function which takes the value of 1 and 0. So SA equal to 1 means if VS is greater than 0 and V1 is greater than VDC, and S equal to 0 otherwise, SB equal to 1 if VS is less than 0 and V1 is greater than VDC, SB equal to 0 otherwise. So II, BIC are the field line winding current of the phase ABC respectively, SASB are the switching function of voltage source inverter. Now coming to DCVR with DC link LC field. So differential equation for inductor current and capacitor VDC, I2 VDC, PI2 equal to V1 minus VDC minus I2 RDC upon LDC, and PVDC equal to I2 minus IDC upon CDC. And the AC mains current IS is given IS equal to in bracket SA minus SB into I2. So where I2 is the current in the inductor, LDC is the filter inductance, RDC is the resistance of the filter inductance, CD is the DC filter capacitance. So DBR with AC series filter, LC filter, the state equations of this topology are PIR equal to VR minus IR upon LR, and PVR equal to IS minus AR upon CR, and I1 equal to Vx minus VDC minus I1 R1 upon L1, PVDC equal to I minus IDC, CDC, and IS equal to SA minus SB into I1. VR is the absolute value of voltage across the resonant filter, and Vx the value of light voltage, and diode is converted to V1 minus absolute value VR, and the R the resistance of the resonating inductor LR. So DBR with series AC passive filter, the difference equation of resonating inductor VR and resonating inductor current IR and capacitor voltage VDC for this topology are PIR equal to VR minus IR on LR, and PVR equal to IS minus IR upon CR, and PI1 equal to Vx minus VDC minus I1 R1 upon L1, and PVDC equal to I1 minus IDC upon CDC, and IS equal to in bracket SA minus V into I1, where I1 is the DC current on pump supply, Vx is the equal to V1 minus absolute VR, and LR are the resonant filter inductance and resistance effectiveness, CR the resonant filter capacitance. So DBR with series AC passive filter and compensating capacitor, the state equations of topology can be given as PVDC equal to I1 minus IDC upon CDC, PR equal to VR minus IR upon LR, PVR equal to IS minus IR upon CR, and PV equal to IS minus IN upon CB, and PI equal to PX minus VDC minus I R1 upon L1, and PI is equal to in bracket VS minus VR minus VB minus IS RS upon LS, and I1 equal to in bracket SA minus SB into I. So where I in is the current drawn by diode bridge rectifier input current, I is the DC link side current drawn from the supply, VB is the voltage across the compensating capacitor, CC is the capacitance of compensating capacitor, LS is the small parasitic inductance of AC, so RS is the resistance of small parasitic inductance. And this is the dynamic response of diode bridge rectifier with capacitive filter fed vector control induction motor. So you can have a supply voltage, supply current, and then the DC link voltage, then the reference speed, HL speed, 3-wise winding current, and the torque, developed torque and load torque. And this is with the dynamic response with the DC side LC filter with vector control induction motor die during starting as well as load application removal. And this is the response with the AC series filter with vector control induction motor die. You can see the supply current and during starting, steady state operation and load application removal. And this is the response AC series LC and compensating capacitor fed, how the supply current is improved during starting, steady state operation, application of load, removal of load. And this is typically the case of starting with the diode bridge with the AC series LC filter and vector control drive. So starting and experimental result, and then typically again for your typically LC with the compensating capacitor ones, the current supply current, and then with the your diode with the LC filter fed, application removal of the load, and this is with the compensating capacitor with the LC filter, how the current is improved supply current along with the motor current, and then the typically with the series filter with response of diode with the AC series filter, and this is with the filter and compensating capacitor, the response is simulator and experimental, and this is the, of course, the harmonic spectrum with the typically you can call it with the DBR with capacitive filter 98%, and with the current with the capacitive filter feeding at the load condition, so TID is reduced with the load, and this is with the LC filter. TID reduces 69%, 69.91, and then supply current TID 53%, and then with the series LC filter, TID reduces 21%, and experimental 25%, and this series with the compensating capacitor, so it goes to 16.9 and exponential 7.4%. Now coming to active shaper. So this active shaper, what we use after diode rectifier, we use the boost converter, we call power factor correction, topology 1. And second is the bridgeless. So here bridgeless means to the one, typically you can call it boost converter operate positive cycle and another negative cycle. The advantage in second is the inductance is shifted to the AC side, and typically we have to sense the voltage and current, and then we have a shaping of the switching of the devices. And these are when we have used asymmetrical lag, and then we have a voltage source converter for improving the power quality. So now coming to topology 1, single switch boost converter. The following the topology consists of DC link voltage controller. The error between the reference DC link voltage and the sense DC link voltage where to PI control the output of an sampling extended I reference equal to I reference n minus 1 plus K PDC VDC minus VD plus Ki VDC into VC. The I reference is N is the output of voltage control at n sampling, and I reference minus is the output of voltage control at n, and the voltage error in DC link is VDC equal to VDC star n minus VDC, and output of voltage after limiting is considered as amplitude of inductor current I reference. So reference inductor current is IDC star equal to I is reference into absolute value of U, where U is Vs upon Vm, where Vs is the supply voltage, can be expressed as Vs equal to Vm sin omega t, and ID star is the reference inductor current of the converter, Vm is the supply voltage, omega is the supply frequency radian per current. So reference inductor current ID star is compared with the sense inductor current ID, and the error is fed to the pendulum current control generally switching signal for the converter devices. Now coming to C, single switch converter. The model of the converter is PID equal to V1 minus VDC into 1 minus S in minus RV ID divided by LB, and PVDC equal to in bracket ID 1 minus S minus IDC by CDC, where AC supply current can be expressed as IS equal to ID into U, where V1 is the absolute value of supply voltage Vs, and AC is the converter switching signal, and IDC is the inverter DC link current, and it is expressed as IDC equal to in bracket SAIA plus SBIB plus ICIG. So now coming to topology 2 switch boost converter, PFC converter. So DC link voltage controller is the error between the reference DC link voltage VDC star and the sense DC link voltage VDC is fed to PI controller. The output of controller and H sampling extent is given as I reference n equal to I reference n minus 1 plus K PDC in bracket PDC n minus VDC n minus 1 plus Ki DC VDC n. The output of the controller after limiting is considered amplitude of AC mains current I reference, and reference supply current generation is I instance reference current IS star is calculated IS star I reference into U, and U equal to Vs upon Vm. So reference supply current is compared with the converter input current, and the error is fed to pendulum current to generate the switching signal for the converter devices. Now coming to typically two switch converter, a set of two first order nonlinear difference equation of the converter current input current and the DC link voltage form the model of the converter as followed. So Pi is equal to in bracket Vs minus VDC in bracket Sx minus Sy minus RVIS upon LB, and PVDC equal to in bracket Is in bracket Is Sx minus Sy minus ID upon CDC, where LB is the inductance of boost converter, RB is the resistance of boost converter, and CDC is the DC link capacitor, and D is the inverter DC link current. So Sx and Sy are the converter switching signal. Now coming to topology 3, asymmetrical two switch converter. So asymmetrical configuration of switch lead to simplified current regulation. So modeling of equation can be written as Pi is equal to in bracket Vs minus Vp minus RVIS upon LB, and PVD is equal to in bracket Ip minus IDC upon CDC, so where Vp equal to VDC in bracket Ss minus Sy and Ip equal to Is Sx minus Lb. Lb is the inductance of boost converter, Rb is the resistance of boost converter inductor, EDC is the DC link capacitor, ID is the inverter DC link, Sx and Sy are the converter switching signal to upper and lower switch just of the same leg of the converter. Now coming to topology 4, single phase voltage source converter. This converter topology consists of following subsystem: DC link voltage controller, I reference I ref n equal to I ref n minus 1 plus K PDC VDC n minus VDC n and plus Ki DC VDC n, and reference current is I instance current I star is equal to I star I is reference into U equal to Vs upon Vm, and the reference supply current I star is compared with the sense input current Is, and the error required to pendulum controller to generate switching signal for the converter devices in bipolar mode. Now coming to the voltage source converter, the model of voltage source converter can be written as PVD is equal to in bracket I in bracket Sx minus Sy minus IDC, divided by CDC, and PI is equal to VS minus VAB minus RSIS on LB, and VAB equal to VN minus VBN, where N refers to negative bus at DC link, and VN is the junction voltage at A with respect to negative DC link bus, and VBN is the voltage in junction B with respect to negative DC link bus, and IDC equal to IS in bracket SA minus SB. And this is typically the hardware implementation of single switch PFC converter fed vector control induction motor drive. And this is the laboratory power circuit of two switch boost converter, the laboratory set of control circuit of two switch boost converter, and these are the simulated digital dynamic response with the single switch boost converter. So you can say supply current during starting, then load application removal, for the supply current in phase with the supply voltage and remains sinusoidal. This is the case for the two switch boost converter. Again, supply current is sinusoidal during starting as well as your steady state, but you can see in starting very drawn small current due to small power drawn from the supply, and then load application, load removal. Then during with the two switch boost converter, so very less current drawn from supply due to very low power drawn by the motor. So you can say three phase motor currents are, you can see increase, but with the limiting current and the load application, load removal. This is the case with the voltage source converter back to control drive. So your supply current increases, and then accordingly reversal take. Here we have a reversal also, couple of reversals. So how the regeneration taking place in the supply side, and this is a simulated experimental performance for typically single switch boost converter, then two switch boost converter, and then your typically how the load application, load removal, and the two switch load application, load removal. Then the harmonics typically with the 7.12 simulator experimental 8.8%. And then with the two switch boost converter, TID is 4.14 simulator, experimental is 4.9 for supply current. And this is typically for two switch asymmetrical, TID is 6.13 at no part load, and typically for full load is 4.3. And then with the typically with the voltage source converter, TID is 5.3% at light load and 4.27 at full load. Now coming to high frequency active wave shaper. So classification of high frequency isolated active wave shaper technique is isolated AC/DC converter, then isolated AC/DC SEPIC converter, isolated AC/DC flyback converter, and isolated AC/DC zeta converter. This is the circuit diagram, schematic diagram, high frequency isolated AC/DC converter. From the supply we use this SEPIC converter here, converter, and here we design the L2 as in discontinuous current mode, which gives the wave shaping in the supply current without sensing input voltage. It senses only DC link voltage and control the DC link voltage, and that's enough to really control this converter. But we get inherent power factor correction and wave shaping on the input, and this is the case with the SEPIC converter. In here also we design again similarly voltage control and design the typically the transformer with the, you can call it in discontinuous current mode. Similarly here in case of zeta flyback converter also we design the transformer inductance in discontinuous mode and control the output voltage, and similarly for zeta converter also we design in the and this is the typical case of your isolated converter where we design the IL2 in discontinuous current mode. This is for typically SEPIC converter where also we design L2 as in discontinuous current mode, and these are the of course the mode we have like a switch conduction, diode conduction, none of the two are conducting, all three modes. And this is for flyback converter. Here also three modes, when diode conducting, device conducting, diode conducting, and none of the two are conducting. Then the zeta converter also LG output is a discontinuous current mode. So we have a device conduction, diode conduction, none of the two are conducting. This is the experimental setup for high frequency isolated wave shaper for voltage source converter fed back control index synchronous PM synchronous motor, and DSP implementation of active wave shaper. And this is the typically you can call it starting performance with the typically with the your AC/DC converter. You can say how the supply current either sinusoidal engage with the supply voltage and speed increases and motor current. This is with case SEPIC converter. The supply current remains sinusoidal during starting as well as normal running condition. And then in case of flyback converter, and then typically in zeta converter also we get supply current sinusoidal and balance. And then the load application, load removal, typically on converter. Then in SEPIC converter also load application, load removal. Then the flyback converter also load application, load removal. And then the zeta converter also load application, load removal. And this is the in case of converter, the supply current is 85.6% and experimentally 5.7%, and SEPIC converted is 3.25 and 4.7 also in experimental. And in case of your flyback converter, it is 3.91, and supply and experimental is 4%. In zeta converter, it is 5.78 and 6% in experimentally. Now coming to case study on design and control of solar PV array fed permanent synchronous motor drive for water pumping system. And these are typical diagram. We have a PV array, we have a boost converter for maximum power tracking, and of course we have a auxiliary load with the single phase converter for feeding the auxiliary load also from the DC link. And the DC link, of course, from the control we maintain the DC link constant and drive this permanent synchronous motor drive for this your synchronous motor drive. And these are the parameter 2.2 kilowatt modes like PMSM. These are of course parameter of local load of 1 kilowatt, and design of PV array, that PV array 3.3 kilowatt is taken and load demand for 3.2 kilowatt motor as well as the 1 kilowatt load, and typically 10 watt modules are used here, and these are the design of the module. So now coming to design of PV array, current at MPPT is calculated PV power 3.3 divided by 360, so 9.12. Number of series connected, you can call it, the modules are 23 and parallel connected are calculated 16. And now design of boost converter, DC link was selected 400 and duty ratio is here calculated 400 minus 360 divided by 400.1, and inductance calculated LDV PV upon S L, it comes 4 millihenry, and the DC link capacitance 280 with 3 VM PM 1 upon root 3 VDC minus 1, it comes to 2009.6 microfarad, so 22 microfarad is selected as a value. So now coming to design of motor side VSI, the voltage rating of IGBT switch is calculated VDC into IDC, that comes 500 volt with the safety, and current rating of IGBT comes into 1 by, so it 2.75, so IGBT of 600 volt 10 ampere is selected. Finally KV rating of PSI is selected, that is 610, 36 kV, and blocking diode of the IGBT used as in VSI also 500 volt and current 7.5, and IGBT selected 600 volt and 10 ampere, and KV rating of VSI 6 kV. And this is MPPT of the PV array. So pattern and observe based MPPT technique is due to simple implementation and the less computational effort. So here it is sense VPV IPV, alert the PV and go to the step change, says the PV voltage and current, and evaluate the power, and if power increasing decreasing, and accordingly reset the duty cycle, increase or decrease, and go back. Now coming control of load side, so ILD equal to ULD into WLD, and VLD VDLD square plus P U1D VLD upon VD, and ID LD star equal to in bracket G1D upon S plus VLD into DVD equal to GIL upon S plus GPL into VLD star minus VLD, and DVLD VLD minus VLD, and DLD equal to IDL. And this is typical control of load side converter. So VLD, what the expression are there, they are implemented for control of output voltage for the switching of the your voltage source converter for feeding the auxiliary load. And this is the control of motor side. So we have a reference speed, two component. One is decided by the PV power control minus LD upon load, PV power minus load power divided by a cube root of that, and LD GI upon DVLD into VDC minus 10 IQ equal to GI. So that gives the typically the IQ corresponding to that. And then we have a control of motor side converter, so DC link voltage control, and we take the power from PV minus load power. So we have a two reference. The DC link voltage control try to, of course, we subtract from the power and we get the reference speed, and then from this reference speed and feedback speed we get the typically the error, and from which we get IQ, and ID we kept 0 for PMSM in lower speed. We have position, we get the 3-phase reference current, and we have a sense current, and give the switching signal for VSI. So coming to sensorless control, VM alpha, M alpha equal to LP IM alpha plus R IM alpha and P pi M, and VMB LMPM M I alpha LM beta P pi M, and pi MB equal to pi PM sin theta ME, and pi M alpha equal to pi PM into cos theta ME. So for sensorless control, P phi MA equal to VM minus LPM minus RLA minus LPM omega E sin theta, and PYM equal to VM minus LPM equal to phi PM omega E cos theta. So we get the phi PM phi the integration of VMD LP minus RX, that's the integration of EM alpha E beta, and theta M equal to tan inverse phi M upon flux, and omega L is a phi ME PL derivative of PML minus derivative of phi alpha phi beta divided by phi M alpha square phi beta square. So this is a typical the implementation of block diagram of presented multi adaptive multi-notch filter for flux observer. Using the, so we have elimination of third 7 harmonic and then get the speed and position corresponding to that flux. These are the equation transfer function of this filter for getting the from the flux observer. These are the, of course, body plot for the for implementation that of the adaptive notch filter. This is the laboratory prototype of the typically of PMSM drive for solar PV array pad. These are the implementation of voltage sensor required for voltage sensing of DC link as well as the typically of PV array. And these are current sensor sensing of winding current as well as the PV current. This is the optocoupler isolation for the typically for the all the converter devices. And this is the implementation of DSP using microlabs. For all the signal of DC link voltage, PV current, and 3 motor currents are sensed for sensorless control. And this is of the correct typically the test result for MPPT for 1000 watt per meter and 500 parts per. These are typically the response for, you can call it load voltage, load current, and the typically the your power, load power, and the motor current. And similarly for the along with the position also we have PV voltage and all the response of phi alpha estimated flux linkage phi alpha phi beta and the position estimation, and for response for change of, so you can call it the PV power and the estimation of phi alpha phi beta and flux linkage, and for the starting response to solar insulation 1000 watt is 500 watt is of course single stage solar array. Here we have removed the boost converter, the inverter able to regulate the voltage correspond to MPPT. And of course the auxiliary load is fed parallel. And so here we have a design of motor side VSI, design of load side VSI, selection of PMSM rating, and selection of local load. So these are typically the model rating PV design. This is the MPPT algorithm, we already discussed it. And this is the control of motor side. Typically of single stage we get the PV power minus load power, and we get the reference speed from load power, and then we have a motor control switching. And these are the equations for your motor control. So omega reference 2 component, one is calculated from power and the calculated from DC link voltage control for MPPT, and then we get the torque reference current from the speed error. And these are typically the experimental wave, typically maximum power tracking performance of solar array at 1000 watt is 500 watt is per. And these are the response PV array, PV voltage, and then the speed and the motor current and the position, then the load voltage, load current. Load voltage remains cancelled in spite of feeding the nonlinear load. And then typically the motor current and the PV array. And this is typically the response during the solar insulation decrease and increase. Now coming to typical design and control of solar PV array and battery pad PM7 drive for water pumping. So here what is used here on DC link, we use the battery which is the power leveling. When you have more generation, you can store the battery and feed the loads also. Even in the night also you can run the pump as well as the load. So here also we have a design of the PV array base, design of motor side, design of load side, and selection of PMSM and selection of local load. So these are the PV array model. We have taken a PV array of 3.3 kilowatt, and these are the design of base. So we consider the backup time of 4 hours with the 3.2 kilowatt requirement. So battery of 2.5 kilowatt hours with DC link voltage of battery voltage of 360 watt volt, and the ampere hour battery of 36 ampere hour. And these are of course the MPPT control, the control of motor side, control of load side, and so this is the experimental setup, and these are the MPPT performance at 1000 watt meter square and 500 of solar simulator. And this is the performance with the base current, PV current, motor current, and the load current. And then typically the position and different parameter load voltage, load current. They during the solar insolation increase and solar insolation decrease the performance. Now this is the case single stage PV array pad battery. So battery is put with the throw buck boost converter, because PV array voltage at DC link we have to keep for corresponding to MPPT and feeding the load. And here we have a design of PV array, design of base, design of, and these are parameters of PV array. And this is the backup time. Similarly we calculate 12.8 kilowatt hours. And DC link here we take now battery voltage 240 volt because of buck boost converter. Rating of again battery of 50 ampere hour. And then the duty ratio calculation or inductor design for the battery. This comes 6.15 millihenry, and the typically the for both the conditions 6.15. So we select higher value. Now control of this buck boost converter. This we calculate outer loop DC voltage loop will be controlled by battery, and inner control will be the battery current. And these are of course segmental waveform for MPPT of solar array at 1000 watt meter is 500 watt meter is car. And these are the typically the total performance of PV array, PV array current, battery current, motor current, and the load current, and then the position in the last, and accordingly load voltage, load current. And this is during the solar insolation typically increase as well as solar insolation decrease. Now coming to design control of single phase grid interface solar PV array fed drive for water pumping system. So here we are connecting the grid and local load, and then the converter, voltage source converter is connected DC link, and we have a PV array also. The extra power is there, then we can feed to the grid also if required, and we can take even the power from the grid for running the pump for 24 hours in this case. So here we have a grid side converter. Is a design of, we consider the DC link voltage 500 volt and grid current about typically of 20 ampere with the power of typically of 3.2 kilowatt and the IGBT rating of 25 ampere, and for we select inverter of 24 kV. Now coming to control of grid side converter. So we have here the DC link voltage control and PV array control, and from load we get the load power. So we calculate the load power. I mean we have a loss component of DC link, and then we have PV array power, that is, and from grid side we get the weight, and then we get the phase from the grid side voltage estimation for peak voltage, and then divide by that. So we get the phase, and we get the supply current reference, and we have actual supply current for getting the usage control for grid side voltage control. These are the equations for power calculation, power weight calculation, loss calculation, and load power calculation, and the total weight calculation, loss plus load minus PV power. We get the reference PV power current, and then the voltage phase, and then we get the reference current. So this is the experimental setup, and these are again MPPT performance set for PV curve at 1000 watt in SCAR and 500 experimentally, and of course the supply current, the PV current, motor current, and load current. And similarly we had a supply voltage, then the supply current, of course PV power is more, the we draw the and load current, then position of the motor, because we are operating in sensorless control mode where it's a submersible, it has to, and load voltage, load current. This is during the increase in solar insolation and decrease in solar insolation. So certainly when solar power increases, so we draw the less current from the grid, as you can see here. I mean like, and accordingly grid power also changes. This is the case when single phase interface with the typically with the fed, the load, local load, and water pumping single stage system. So these are of course the design in the same way, and these are the experimental result for MPPT for 1000 watt and 500 watt meter square, and the experimental result for supply current, PV current, supply current, load current, and the motor current, and the position typically, and for sensorless control, and typically variation solar insolation increase, then current, supply current decreases, then typically power down from supply also decreases as the PV current increases. And then coming to design control of single phase grid interface solar PV array, battery fed. So here we have a battery which is smoothing the power of PV variation, load variation, as well as the grid availability and non-availability. So you get uninterrupted operation of the water pump. So these are the, of course, the experimental setup, and these are the MPPT performance correspondingly for 1000 watt, 500 watt. These are the performance, supply current, PV current, motor current, and the load current, and then the position, then the load voltage, load current, and all performance parameters. And then for increase of the solar power, decrease of solar power, so accordingly grid power changes. And then the typically how really typically for at 1000 watt meter is and 500 watt meter is car. Then increase on solar insolation and decrease on solar insolation. Then now this is the same where we have a single stage, but battery we keep at DC link with the buck boost converter, so that you can regulate the DC link voltage for MPPT. And then we have a grid availability, non-grid, so we can isolate from the grid also. So these are the rating calculus, and then we have a control of synchronization unit. So this is control of synchronization unit. We have sense voltage and load voltage, and we calculate the angle. And once we want to grid appears, we synchronize by moving the inverter towards the grid. And finally, when angle frequency and voltage, then we close the switch like. And when grid disappear, we open the switch. So this is typically the control of synchronization. I mean, how the angle calculation, how the voltage calculation, and how the frequency calculation take place. And then the block diagram of your filters for the typically for estimating the your V alpha beta even distorted grid is there, you operate that and get the angle as well as the magnitude of the voltage. And these are performance at 1000 watt, MPPT performance 1000 watt and 500 watt meter square. And this is the case when your typically the solar power increases, so grid power decreases, dynamics, and accordingly typically the position and as well as the motor current, grid current, load current all are shown here. I mean, when the grid is not available, that also system works very perfectly. And then the synchronization islanding, in islanding case, and this is the case of synchronization when grid appears, and then we synchronize this to the typically from the grid, the system. Now coming to design control of three-phase grid interface PVRA system. This is where we have a three-phase grid and typically three-phase load, local load, and then a voltage source converter, and then boost converter with ambient. So extra power is generated, then it fed to the grid, or we can take power from the grid to uninterrupted operation of the pump drive for 24 hours. So design of grid side converter, this is voltage, VSI is considered 500 and according rating are selected. And this is the control of the grid, typically the grid side converter. We have a load null, maybe null here, so we can filter the fundamental current, and then we have a weight corresponding to that, so we have calculated the load power, then DC link voltage control, we get the loss component and the PV power that gets subtracted. It may vary accordingly, the weight is decided. Then with the amplitude of the grid voltage, we calculate the grid reference current, we sense the grid current and current controller for the voltage source converter. And these are of course the filter equations for the grid voltage filtering if they are distorted, and these are the grid current reference current calculation correspond to different way. And this is the laboratory prototype. And these are the typically your performance of MP solar PV curve at 1000 watt and 500 watt square. And these are the typically, you can call it the PV where the grid current, then motor current and the load current. Typically three-phase load current comes quasi square way, the position and the motor current and the PV voltage and speed. And during typically when PV power increases, grid current reduces, and accordingly the performance is varied. So now the another case is corresponding when really we have a single stage system of PV array. So here we have to control the converter corresponding to, so that it is the MPPT. So this is the MPPT, typically MPPT performance 1000 and 500 watt meter square. And here you can just see here the PV current source, grid current is not there, and the motor voltage and load current, and accordingly position as well as motor current, PV current and speed. And during the when solar insolation increases, supply current decreases. Accordingly, the variations are shown here, all parameters. We're going to design control of three-phase grid interface solar PV array with battery. So here we connect the battery typically on the DC link with the boost converter. So we maintain the DC link voltage constant typically for feeding up reliable power to the battery as well as grid is there. When the battery is responsible for you can call it the intermittency of the solar, intermittency of the grid, intermittency of the load as well as intermittency of water pumping. So then it's a laboratory. So these are the experimental waveform of PV curve at 1000 watt apart, 500 watt meter square, and here is the performance of PV array mode, grid current, motor current and load current, and then the position, PV current and the motor current during solar insolation increase decrease, and then the typically when the grid is not available, then the operation, then when the dynamic operation when grid is not there, then we connect the battery with the single stage with the buck boost converter, and the grid synchronization islanding is also taken here. So it's a design for grid synchronization again voltage, the frequency of grid as well as load is voltage source converter, and that is plotted towards that. So comparing the frequency, angle and typically voltage. So and this is angle calculation how the synchronization takes place. Then the typically the control of the grid side converter, and this is a performance at 1000 solar PV curve performance at 1000 watt meter square and 500 watt meter square, and the experimental performance corresponding to typically how the grid voltage and grid current, load current and PV voltage, and then accordingly the load voltage, load current, grid current, grid voltage, grid current is sinusoidal, load current is non-sinusoidal, and PV voltage and the position and motor current for islanding mode operation also, and typically, and then synchronization. These are typically how we synchronize to the grid. Load is not affected. So coming to the solved problem. Yeah, example 1, a PMSM drive has the following specification: 7.5 kilowatt, 3-phase 415 volt, 50 Hz, 4-pole star connected, XSD 2 ohm, XXU 10 ohm, rated power factor 0.96 lagging, permanent flux linkage 1.02 volt second, and negligible resistance, so neglect friction voltage, current core loss. The speed of motor is controlled using indirect vector control scheme using PWM BSI. The motor is controlled with constant flux below base speed and constant rate voltage above the base speed. To calculate the reference DQ current component of the hysteresis current at starting, if starting torque is required equal to the rated torque, so LD equal to SD upon omega E, so that is 6.33. LQ similarly calculate 31 point, and TR is 47, lambda P 1.0, and similarly the motor control rate is starting 0 speed, the flux is obtained, so TST 47 point, and that equal to this. So from this we calculate IQ equal to 15.52. Coming to example 2, a PMSM drive has the following specification: 7.5 kilowatt, 3-phase 415 50 Hz, 4-pole star connected, XD 2 ohm, XQ 10 ohm, and rated power 0.9, permanent flux linkage 1.02 volt second, and negligible resistance, neglect friction voltage and core loss. Speed of motor is controlled using a direct vector control scheme and using PMSM PWM BSI. The motor is controlled with the constant flux below base speed and constant rate voltage above it. So calculate the difference DQ component of hysteresis current and hysteresis frequency at half the rated torque and half the rate. So LD is calculated omega ST upon omega E 6.33, LQ 31.9, TR equal to 47.75, lambda equal to 1.076, and since the motor is operated at base speed I equal to 0, so T equal to 2.23, half the rated torque, and from this we get the IQ equal to 7.762. So coming to example 3, the specification of PMSM drive are 7.5 kilowatt, 3-phase 450, 3300 4-pole star connected synchronous induction is 3.5 millihenry, and the rate induced open at 2500 rpm. If this motor is running at 1000 rpm and 85% of rated in the field oriented control mode, calculate the quadrature access mode, resultant armature flux linkage with direct access equal to current 0. So here all the data are given. So calculating A for simulation, omega R equal to pi by 30 into 6000, 110 omega E R equal to 220 radian per second, and TR equal to 21.7. So VOC 239 points, 2500, Y equal to 5, then omega E equal to 526.6 radian per second. So the flux linkage root 2 VOC upon omega E, so it comes 0.64715 Weber, and T equal to 0.85 TR, that is 18.75, and T putting this, so we get IQ equal to putting value 9.5 ampere, and ID equal to 0, so lambda equal to lambda PM equal to lambda Q LS PM, and lambda D equal to under lambda square Q square, it comes 0.648 Weber. So coming to example 4, a 25 kVA 4000 222 phase 3-phase permanent synchronous motor producing rated open circuit voltage at rated speed of 3000 rpm and has a synchronous inductance of 1.75 millihenry. Assume the motor is operated under field oriented control at 2600 rpm and 65% of rated torque. Calculate the required Q access current. A controller is designed to minimize the armature current by setting ID equal to 0. Calculate the resultant armature flux linkage in per unit. So solution is the rated speed of the motor is 419 radian per second, and rated torque is your 59.7 second, and open circuit voltage is 230 by root 3 127 at speed 3000 rpm. The corresponding omega equal to 335 radian per second, and equivalent circuit LAF IF, that is product is lambda PF, that's 0.536, and T reference equal to T rated 38.10. So we get the Q access current IQ equal to 2 by 3 T reference by delta P, so it comes 48.3 ampere, and with the ID equal to 0, lambda equal to lambda PM, that is 5.36, so lambda Q equal to ILS IQ comes 0.46, so the flux armature flux is lambda D square lambda Q by 2, that is 0.38, so base armature flux is P upon, that is 0.32. So since voltage is 127, omega is 419, so thus the flux per unit armature flux is 0.38, so 1.27 per unit. So example 5, 25 kVA 4000 rpm for 220 volt 2-pole 3-phase permanent synchronous motor producing a rated open circuit voltage and rated speed of 3000 200 RPM and has a synchronous inductance of 1.75 millihenry. Assuming the motor is operated under field rate control at 2800 RPM and 65% rated torque. If the controller is designed to maintain the armature flux linkage at its rated value, the calculate the corresponding value of ID and corresponding RMS and per unit value of armature current. So solution: in order to maintain armature flux linkage rated value lambda base, direct flux linkage shall be lambda d equal to under root 2 lambda a square base minus lambda q, that is 0.42 Weber. Therefore, LD equal to LS and ID reference equal to lambda d minus M divided by LS, to minus 66.3 ampere, and ID equal to under root IDI Q reference by 2, that's 58 ampere. The base RMS current I base P base under root 2 becomes 65.6 ampere, and per unit armature current I upon I base, that is 0.88 per unit. Now coming to example 6, a PMSM drive has the following specification: 3-phase 1.93 kilowatt, 3325 RPM, 4-pole star connected, LD equal to 9.1 millihenry, LQ equal to 11.5 millihenry, and J equal to 0.2015 km square. Flux linkage is 0.91 volt second. R equal to 1 ohm. It is controlled in vector control mode with the boost converter fed from a 96 volt DC source and feeding a VSI at 400 volt DC bus. Calculate the following at starting. If starting torque is required equal to the rated torque, reference DQ component of starter current, average DC bus current, RMS current at starting. The starting torque required is the rated torque. The rated torque is T rated period of 5.54 Newton meter, T rated 3 by 2 P by 2 5 M IQ. So putting value, it comes IQ equal to 9.66 ampere, and since the motor current controller at starting, the flux is from PMS and DX is 0, therefore IM equal to under root IQ square R by 2, that is 6.83, and since the motor is at 0 speed, the motor power is 0, on the other loss is opening instead are supplied through other root T into omega P loss equal to 3 IM square RS, so it comes pure 139.94 watt, and the average DC current IDC PDC upon VDC, it comes 0.349 ampere. Now coming to example 7, a PMSM which has the following specification: 3-phase 48.6 kilowatt, 700 RPM, 8-pole, star connected, L equal to 2.8 millihenry, J equal to 0.134 km square, flux linkage 4.8 second, R 82 millihenry, and is controlled in vector control mode with the boost converter fed from 360 volt battery and feeding a this VSI at 750 DC. Calculate the following when the motor is operating 500 and 80% of rated. So reference DQ current, component of starter current, average DC bus current, RMS starting at. So solution is starting torque required and 5 times the torque. So rated torque is P rated upon 3663 Newton. So thus typically the T equal to the, so putting a value, IQ comes to 18.4. Motor current is IM equal to IQ equal to 2, that is 13 ampere. And power input is the motor current P loss into omega plus 3 IM square, so it comes 27.7 kilowatt. Average DC current PDC VDC, it comes 37 ampere. Coming to example 8, a PSM which has the following specification: 3-phase 34.6 kilowatt, 575 RPM, 8-pole, star connected, L equal to 2.5 millihenry, J equal to 0.1985 km square, flux linkage 5.6 volts, R equal to 84 millihenry. It is milliohm. It is controlled in vector control mode with the boost converter fed from the 380 volt battery and feeding a VSI at 565 volt. Calculate the IP starting voltage. Starting torque is required equal to the 3 times the rated torque. Reference DQ component starter current and average DC bus current, RMS current at starting. So solution is starting torque required in 3 times the rated torque. The rated torque is T rated P rated to 576.6, and thus putting typically 3 times the rated torque. In this, the IQ comes 51.3 and motor current is IM under QS of 36.3 ampere. Since the motor is at 0 speed, motor power is 0, only losses occurring instead of this supply. Moreover, the losses T equal to 0, so P loss equal to 3 IM square RS, that comes 32 kilowatt, and average DC bus current is IDC PDC VDC, so it comes 0.5876 ampere. Now example 9, a PMSM which has the following specification: 3-phase 34.6 kilowatt, 575 RPM, 8-pole, star connected, L equal to 2.5 millihenry, J equal to 0.1985 km square, flux linkage 5.6 volt second, and R equal to 84 milli ohm. It is controlled in vector control mode with the boost converter fed from 380 volt and feeding a VSI at 565 DC volt bus. Calculate the following when the motor is operating 200 RPM and 250% of rated torque. So reference DQ component of hysteresis current, average DCS current, RMS hysteresis current at starting. The solution is starting current, starting torque required is the 3 times the rated. This is T rate equal to P rated. So this is 576 and developed torque is 250. So T is this, so IQ is 42.75, motor current is under root IQ square by 2, that's 30.2, and power input to the motor T omega to 3 ms square. Putting a value, it comes 30.316, and average DC current DC over DC comes 53.66 ampere. Going to example 10, an 8-pole interior PMSM is operating in a forward motoring mode, and the develop a output torque of plus 324 Newton meter at 1500 RPM. Split the magnet and reluctance torque at 165 Newton meter and 155 Newton meter. Let the per phase resistance are S equal to 69 milliohm, and let the no load torque TNL equal to 0. Let the inductance be LMD equal to 1.6 million, LMQ equal to 2.6 million. At this condition, the machine constant equal to K equal to 0.36. To determine the DQ axis current, applied voltage per phase and current, machine efficiency. So the rotary speeds in a hertz time recurrence are omega equal to 2 pi NR upon 60, 157.08 radian per second, FR equal to omega upon 2 pi, that is 25 hertz. The electrical input frequency omega equal to P by 2 omega, so 628.3, and P equal to 100 hertz. And magnet and reluctance torque, both T PM is 165 and TSR is 159. Electromagnetic torque is TM equal to TR TNL, so 324 plus 324, the per phase cardiac access is equal to TM 3K, that is 152.8, and then per phase direct access by VDU 2 TSR from LMQ, LMD minus LMQ upon IP, it comes to minus 86.7 ampere. And the supply current per phase IP is IPD square plus IQ square, so it comes to 175.7 ampere. And vacuum of the PH K omega R, that comes 56.5, and cardiac access component supply voltage PH equal to PHR SIS omega LMD, so it comes to minus 20.1 volt. Direct access component of supply voltage is minus 1, so it comes minus 255.6, and supply voltage is each under root TH square DQ square, so putting value 256.4 volt. And PR equal to TR omega 50.89 kilowatt, and machine power loss in the sum of total TR and 3 omega, so it comes 6.39. The input power to the motor is PR plus loss 50.89 6. So it's 57.28, and motor efficiency PR upon P, that comes 88.84. These are the references from which this lecture is prepared. Thank you.